Hello all, today we're going to be looking at our last section of chapter 4, which is actually solving the separable differential equations. The differential equations class, which usually comes after Calc 3, is a class that is completely devoted to solving these types of equations. I'm going to use spooky colors because it's close to Halloween. So differential equations that just have a y prime in them. Now, all of these examples right here, we can actually separate the dx from the dy. So for example, like this one right here, I can write my y prime as dy over dx, and it is equal to y. So I want to get all my y's and dy's on one side, and then my dx's on the other side. So if I multiply by dx, that will get rid of this, and then I can divide by y, and I will actually have a 1 over y dy is equal to, there's a placeholder 1 for our dx that we have there. So this is separable because we can separate our x's from our y's. These examples down here, we can't actually separate our x's from our y's. Someone would think that maybe I could subtract this y, but then the relationship that is happening to my dy over here is an addition and it needs to be a multiplication. So these are actually, we'd have to solve these a different way, and you will get to that if you take differential equations, usually after Calc 3. So let's look at this example. This example looks like down here that it would not be separable, but it's a little bit tricky because both of those terms have x's. So if I actually factor out an x, I'm going to write my my y prime as dy dx over here. I can actually change this into being separable because I can keep my x over here. I can multiply by dx on both sides. And then I can also divide by this 1 plus y. So I'd have 1 over 1 plus y dy. And then now all my y's are on one side, all my x's are on the other side. I could potentially actually take my integral. I know this question is only asking us to tell if this is separable. And we have some steps below here that actually show us what is happening in an example of this. But I'd rather just continue doing this problem right here and show you what it means when we're trying to find a solution to a differential equations problem. So if I take my integral of x with respect to x, remember x is my variable that I'm trying to take it with respect to, I would have x squared divided by 2 over here on my side. Now I would also have a plus c. I'm just going to write it as a plus c. And if I do the same thing over here, take my integral of 1 over 1 plus y, that's actually going to be ln of 1 plus y, because if I take my derivative of ln of 1 plus y, I would end up with this 1 over 1 plus y right there. Because there's nothing in front of the y, we don't have to use substitution or anything, so this is essentially just getting multiplied by 1, which doesn't change it at all. And over here on this side, I'm also going to have a plus c. Well, it is kind of confusing. Maybe I'll do this like as a c1 and this is a c2, but they're both just constants. So if I am adding two constants, I can just combine those constants together and make like a new constant. So we don't usually write this constant on my y side. I would just have like ln of 1 plus y is equal to 1/2 x squared. And then if I combine both of those constants, I would end up with a new constant. I'm just signifying it as c3, but it's just a constant. I could just have a plus c right there. We are almost done because the last thing that we need to do is actually solve for y in this case, because equations are solved for y. So to cancel out this ln, I am going to raise e to the power of that on both sides. So I actually have 1 plus y is equal to e, and then all of this is in my exponent, and I would have like a plus c3 right here, but when I'm adding stuff in my exponents, that is the same as actually multiplying them. So I'm going to rewrite this plus c to the third as e c to the third right there. And now I have a e to some constant, which is going to be another constant. So I'm going to rewrite this as just, let's say, c to the fourth, which is just some constant. I'm signifying it as a different constant, but it is just some constant that I have there. Hey, I'm actually almost done because the last thing that I need to do is subtract 1 from both sides, and now I have officially solved for my y. Now, you may notice that there's still a constant right here. If I were given some initial value like y of 0 is equal to 1 or something in this problem, I could plug in 0 for my x, set my y equal to 1, and solve for that constant. But I'm not given this, so we call this a family of solutions instead of a particular solution. So if I used this initial value, that would be solving for a particular solution. Here is another example of going through a solvable separable differential equation, so you can kind of follow through on that. Again, I want to reiterate, we only need one c on the right. It could have been on the left, but we just chose on the right because we were solving for y, and it makes our life a little bit easier because the constants that I get from both of these integrals right here can be combined into one constant to rule them all. So both of these examples are pretty similar to the one that we just did above. I did want to, however, we're not going to go over these, but I did want to give you the answers so that you can check them on your own. For the first one, before we actually solved for y, this would be your answer. So like separating them out, the y is on one side, the x is on the other side. This would be your answer that we would get. And then to solve for y, I would want to take ln of both sides, or divide by negative and then take ln on both sides to get this final answer that I have down here. The second one is looking at a particular solution instead of a family of solutions. So this one's a family. This one would be a particular solution because it is going through, it gives us this initial value that we would have. I actually want to look at this last problem because it does both of those things. So it's kind of a better summary of the two that are above. So I'm going to rewrite my y prime as dy dx, and I'm trying to separate my x from my y, and luckily with exponents, I can do that through multiplication. So I can rewrite this as e to the x times e to the y. And now I'm going to get my e to the y on this side by dividing by it. So I'll have 1 over e to the y. Maybe I'll just write that as e to the negative y, dy on that side. And then I'm going to get my dx on this side by actually multiplying it. So on my right-hand side, I will have e to the x dx. Now, all my y's are on this side. I can take my integral. All my x's are on this side. I can take my integral of that. I'm just going to start out on the right-hand side because my integral of e to the x is just real easy. It's just itself plus a c. And then almost the same thing over here, except that using chain rule, the derivative of e to the negative y is going to pull a negative multiplying out in front. So I want to be able to cancel that out to get a positive right here. So I'm going to have a negative out in front of there as well. And then again, I don't have to have a plus c on this side because my constants have combined to form this mega constant. I'm trying to solve for y, so in order to do that, I'm going to multiply everything by -1. This c is a constant, so it's just absorbing that negative. It'll just become a negative right there. And I'll have e to the negative y is equal to negative e to the x plus c. And I could represent it as a different c, but I'm just going to leave it as a normal c. Okay, so next, I'm still trying to solve for y. So to cancel out that e, I'm going to take ln of both sides. So I will have a negative y over here is equal to ln of negative e to the x plus c. And I think the last thing I need to do is actually multiply by -1 to cancel those out, and that will just make this negative over here. So this is my family of solutions, but I want the particular solution that is going to go through this value. So I'm going to plug in 0 for my x and 0 for my y. And I will end up with, let's see, that'll just be a -1 plus c right there. That's a 0 to cancel out that ln. I'm going to do e to the this power. So I will have e to the 0 is just 1 is equal to -1 plus 2. So c is going to be equal to 2 there. And my particular solution will look like y is equal to negative ln of negative e to the x plus, instead of just a constant, it'll be plus 2 right there. Okay, we're going to be looking at, the cool thing about differential equations is that there's a lot of physics applications to them. So this is a great physics application. It's Newton's law of cooling. Basically, Newton's law of cooling says that the rate of temperature, the rate that the temperature is changing over time, so the capital T is temperature, the lowercase t is over time, is equal to this, where this is some k constant. My T of S is my like a temperature or ambient temperature that is in the room. And then I can, this is a relationship that occurs between all temperatures. So I want to look at this problem down here where we have a pizza that is coming out from the oven, and we are trying to, when it comes out of the oven, so some important information here. When it comes out of the oven, it is 200 degrees. So that's kind of like an initial value that I'm given. So when time, so this is my capital T is temperature. My temperature at time 0 is going to be 200. And then we have some other information here. So the temperature of the kitchen is 75. That is going to be like my T of S up here. And then after 1 minute goes by, the temperature of the pizza is 190. So that's another like almost initial value, or we're given the temperature at T equals 1, so 1 minute in, it has cooled to 190 degrees. How long will we have to wait until the temperature of the pizza reaches 150 before cutting and serving it? So we are looking for the time that it takes for it to be 150 degrees because we don't want to burn our mouth. While the pizza is coming out, we're going to do all this math to figure out when we can eat it. So I'm going to set up my differential equations here. I don't know what my constant K is. I don't know what my temperature is, but I do know that my ambient temperature, the temperature that the pizza came out into, that T of S is actually my 75 right there. It doesn't feel like we have enough information to go by, but because we were given all these initial conditions over here, I'm not too worried about it. We'll be able to solve for this K constant, and we'll also be able to solve for our C constant when we actually take our integral. So I'm going to treat this just like I was before, where I get all my capital T's on the same side and all my lowercase t's on the same side. So I'm going to actually divide this whole thing by T minus 75 as a whole. So T minus 75, I'm getting my capital T's over there. So I'll have 1 over T minus 75 dt is going to be equal to K dt. And this K is just some constant. So if we think about taking our integral of some constant with respect to time, that is just going to get multiplied by that variable. I can double check this. If I take my derivative of kt with respect to t, I'll just get back to this k. So I know I did that correctly. And then I'm going to have a c over here, which is also a constant. Okay, integral of this is going to be ln of t minus 75, and I can always check that by taking my derivative of this, and I should end up with 1 over t minus 75, which I do. Now this is just a matter of solving for what our capital T is. So I'm going to raise both sides to the power, or e to the power of that, and I will have t minus 75 is equal to e to the kt, and then I will have this written as e to the c, which I will rewrite as a new constant. So I'm going to rewrite this as a new constant. We'll just call it c1, and then that's still getting multiplied by e to the kt. I think last thing I need to do is just add 75 on both sides. So now I have a weird equation, but it has two unknowns. It has two constants. If I think about this, I'm actually given two initial values. I'm going to start out with the first one that was given. So if I plug in 0 for my time, my temperature should be 200. So 200 temperature, and then I'm going to plug in 0 for my time. This is not going to actually help me find my k because 0 is multiplying by my k, but this will help me find this constant, this C1 that I'm looking for out in front. So that'll be 125 when I subtract 75, and then c to the 1, and then e to the 0 is just going to be 1. So I have just solved for what my C1 is going to be. I'm going to replug that in to this equation right here. So I have t is equal to, now I know that my C1 is 125. That's good. And then e to the, I still need to solve for that k constant, which I have not used this other initial condition that was given to me. I'm going to use that now. So when my time is 1, so k times 1, my temperature is going to be 190. Okay, if I subtract 75 from both sides, I'm going to get 115 over here is equal to 125 e to the k. And I'm trying to solve for k. I will get rid of this 125 by dividing it. And then I think the last thing I'll need to do is take my ln of both sides to cancel out that e. And then I will have solved for k. So k is going to be equal to ln of 115 over 125. It is actually better to write your k value as this ln of 115 over 125, but if you round it to at least like 4 or 5 decimal places, it shouldn't make a difference. Our whole question was, how much time is it going to take me in order for the temperature of the pizza to reach 150, and I want to eat it? So I now have an equation that has no constants because this is going to be e to the, I'm going to just leave this as ln of 115 over 125. And then that is getting multiplied by my time. That's what I'm trying to solve for, plus 75. It may seem like this e and this ln could cancel out, but that is not the case because this ln is attached to my t, so I can't actually do that. If we do set this to 150 over here and actually solve out for my t, I'm going to let you do that on your own. We should get that t is approximately 6.12 minutes. So there would be a little bit of work to actually find that. I'd subtract by 75, divide by 125, take my ln of both sides, to solve for what my t value would be, which is about 6 minutes. I wish my pizza would cool faster so I could eat it faster. Okay, y'all, we have another physics problem in here, and this is actually maybe more of an engineering problem. So we have there's salt water initially in this tank. So salt water, or actually, sorry, there's no, Okay, y'all, we have a kind of physics, but mostly engineering problem here. We have a tank that is full of fresh water, so it contains 6 liters of fresh water. And we also have salt water. So salt water containing 1 kilograms liters of salt is pumped into the tank at this rate right here. So this is the rate and the amount of salt that is in that water that is getting pumped in. And then at the same time, this is getting pumped out. So like salt water is coming in, it's immediately mixing with that fresh water, and then we have it coming out at, it happens to be the same rate. So we are trying to find a formula for the amount of salt in the tank as a function of time t. The first thing that I'm going to think about is I'm going to define a function. I happen to find it be a U. That's kind of common, but it has nothing to do with U substitution. So I'm going to let U of T actually be the amount of salt in the tank, which if I define that as the amount of salt in my tank, then I can think about my rate of change of that salt. So how the change is occurring of salt in there. That's what my du dt is going to be. So now that I've kind of defined those, I am going to also state that I am given an initial condition. So the amount of salt at time 0 is also 0. Now I'm going to think of this du dt with some things happening to it. So it is impacted by my inflow rate, and then the amount of salt that is in there with respect to time is getting taken out. So I'm going to subtract out my outflow rate. Now finding the inflow rate, that's actually not too bad because this is the amount of salt that is in there. This is how much water is getting pumped in, so that's the rate. So if I actually multiply those, that will give me the amount of salt that is coming into the tank. My liters will cancel out, and I will have 2 kilograms per minute of salt coming into my tank. So that's my inflow rate, but my outflow rate is not just a rate of, it's not just like this 2 liters per minute. It has to do with that, but we're thinking about the amount of salt that is flowing out. So I'm going to have to do a little more calculation to find that. Okay, and in order to think about that, I don't actually know how much salt is going to be there all the time, but I did define the amount of salt in there to be U of T. And since the rate is 2 liters per minute flowing in and out, that is going to be diffused amongst the 6 liters that is already in there. Okay, and so that is going to be my amount proportional salt in tank. And then I'm going to multiply that by the rate of change that is occurring. So the outflow. And my liters will actually cancel out. I will get U of T divided by 3, and this is also kilograms per minute. To make my equations just a little bit easier, I'm not going to think about the rates or like the kilograms per minute, the units that I have there. But I do want to somehow combine these so that I can make this a separable differential equation, since I want to separate my U's and my T's all on the same side. So what I'm going to do is actually multiply that 2 by 3 over 3. I'm just multiplying it by 1 so that I can have the same denominator over there. So now this 6 minus my U, they're kind of attached to each other. So I can get that on my other side by dividing by it. So I'll have 1 over 6 minus U over here, and then I can also multiply by dt on this side, which will give me this now separated out differential equation, which is great. Now I can take my integral. I'm going to have to be careful of my integral on the left-hand side because there is actually something in front of that U. So you can either use U substitution, which would be weird because there's already U here, or we can just think about it really hard and know some things about derivatives. So if I take my derivative of ln of 6 minus U, I will almost end up with this. I will end up with 1 over 6 minus U, and then I will have to take my derivative of the inside, which will multiply this by a negative. So I want to cancel out that negative. I'm going to put a negative out in front of here. And I will just have 1/3 T plus C on this side. Y'all, we are almost there. I just need to solve for U. If I solve for U, that'll give me an equation of the amount of salt that is in the tank at any given time. So I'm going to do a few things kind of all at once. I'm going to multiply by -1. So -1 will get multiplied over here. And I am also going to take now that this is positive, I'm going to take e to that power. So I will end up with negative 1/3 t plus c in my exponent, but I'm actually going to rewrite this c right here. When it's like e to that power, it's going to be a different constant. So I'm just going to multiply it by a constant in front of that e. So this will be the only thing actually up in my exponent. I think all I have to do from here is just subtract 6 and divide by negative 1 to find u. So I end up with u of t, so the amount of salt with respect to time being this function over here. I want to solve for that constant, what I have labeled as c sub 1. And if I remember, there is no salt at the very, very beginning. So I can actually use that equation, this initial value problem, to solve for what my c is going to be. So I'm going to plug in 0 for u minus, this is my c sub 1, and then e to the, this will be a 0 times 1/3, so just a 0. And I think that I will get that c is going to be equal to 6. So my entire equation will look like 6 e to the 1/3 t and then plus 6. Okay, y'all, I hope you have a beautiful day. Look more up on Canvas if you're looking for any help with some of the homework questions. Okay, bye.